Welcome to the Crazy Hat Chemist. So here's another video on kinetics. We're going to do another example and hopefully we have a good fast rate law here for this one. So let's get moving. Bam! So today we're deriving the rate law and the rate constant. This is example number 3. So make sure that you review example numbers 1 and 2 before carrying on with this one. It gets increasingly more difficult. We're going to derive the rate law and the rate constant, that is the K, for the following reaction. Here's this reaction right here. And notice with this reaction, we're going to derive the rate law and we only are going to be looking at the reactants. We're not going to be looking at the products because the rate law is only in relationship to the reactants and a catalyst if that is involved. Okay, so right here is a set of data. It says the above reaction was studied at 26 degrees and the following data was collected. You should see that I've got a number of columns here. The first column on the left, I'm going to move from the left to the right. First column on the left is experiment numbers 1 through 7, and correspondingly I have concentrations in moles per liter of each of the 3 reactants. H2SeO3, that's the first column with concentrations. The second one is the hydrogen ion concentration. The third one is the iodide ion concentration for concentrations. It's not in the same order as what is the reaction, but that really doesn't matter as long as the numbers coincide with what those concentrations are and what those elements or compounds are. And then the last column on the far right is the initial rate, and that's moles per liter seconds. Okay, so what we're going to do is we need to derive the rate law. And remember, the rate law is only with relationship to the reactants. So that means that the rate law in the skeleton form is like this. The rate law is R is equal to K, that's the rate constant, that's the K, and then it is concentration of H2SeO3 to the power of X, and that is the order of that, and I need to find that. And then it is hydrogen ion concentration to the power of Y. I need to find the order for the hydrogen ion concentration, and that would be Y. And then the iodide ion concentration, and then to the power of Z. And that is the order of the iodide ion concentration. I'm trying to solve for that as well. So I'm going to find a set of reactions in which only one reactant is changing and the others are being held constant. So what I want you to do is I want you to pause the video right now and right after I give a little bit of direction, that is, and then figure out which 2 sets of reactants and remain constant while the other one is changing while the initial rate is changing. Okay, so let's start this off. This looks like a complicated problem, but it's really a simple puzzle as long as you do it one step at a time. Okay, so what we're going to do is we're going to do the first one here, and we're going to find 2 reactions, or 2 reactions. It happens to be experiment 1 and 2, in which 2 of the reactants are being held constant, and that's why I've redlined them out here for you. Okay, so with experiment 1 and 2, the hydrogen ion concentration and the iodide ion concentration are being held constant. And now I'm going to look at the H2SeO3. Okay, and with this, with experiment 1 and 2, there's a doubling of the H2SeO3. Okay, now I'm going to look at the initial rate and find out what's happening with the rate. Okay, as I double the concentration of the H2SeO3, what happens to the rate? It also doubles. Okay, so that is, if I have 2 to the first power, I get the number 2, and that is first order. Okay, and that's why I just solved for the exponent here of x for the H2Se. That is the order of the H2Se, and that is first order. Okay, so 2 to the first power, that's the first order, is equal to 2, and that lets me know that it is first order. So 2 is the doubling to the first order, the order is equal to the initial rate, and that's 2. All right, so we're going to erase these red lines so that we don't get any confusion going on there, but I'm going to keep the doubling and doubling there in the blue. So I just erased that. Now what we're going to do is find 2 other sets of reactions, experiments, in which 2 of them are being held constant. Now again, I already got the order of the H2SeO3, so hopefully I'm going to find 2 reactions in which this is being held constant, as well as either the hydrogen or the iodine, and I'm going to pick the iodine in this case here. So I'm looking at experiments 1 and 4. And with 1 and 4, I'm going to look at the hydrogen ion concentration and figure out what's happening between experiments 1 and 4. And this is a doubling of the hydrogen ion concentration. Now I'm going to look at the rate column and look at experiments 1 and 4. And looking at experiments 1 and 4, what is happening to the rate? The rate is going up by a factor of 4. So 2 to the second power is equal to what number? 4. So 2, that's a doubling of the concentration, is equal to the doubling of the concentration to the power of 2 is equal to the quadrupling of the initial rate. And that tells me the order of this reaction, which is, of course, second order for the hydrogen ion concentration. Okay, hopefully that's not too bad. Okay, remember that is 2, that is the doubling of the concentration of the hydrogen to what power equals 4, and that happens to be a 2, and that's the order. All right, so let's look at the next one here. We're going to wipe those out. We're going to take another set of 2 experiments here that we're going to compare, and this time we want the iodine ion concentration here that we're trying to derive. So we're going to look at experiments 1 and 6, and experiments 1 and 6, the H2SeO3 and the hydrogen ion concentration are remaining constant, and that is very important here. Okay? All right, so now we're going to look at the doubling here of the iodine ion concentration between experiments 1 and 6. And then we're going to need to ask ourselves, what is happening to the rate between experiments 1 and 6? So the rate is going up by a factor of 8. Now, in previous lectures here on kinetics, I talked about sticking with a 0 order, first order, and second order. But I've expanded this on to another type of order, because remember, it can be fractional coefficients, it could be negative values, and 0, 1, and 2 are not the only ones. Now we're going to predominantly stay with just these 3, 0, first and second order, but we've expanded this for this problem here. So doubling of the concentration of the iodine, so 2 to what power is equal to 8? 2 to what power is equal to 8? 2 to 3, that's the third power, is equal to 8. So this is a tripling. Okay, now, so this is iodide ion concentration is a tripling. Okay, it's to the third power. The order is 3. Now, the overall order for this reaction is the sum of the 3 numbers. That's 1 plus the 2 plus the 3. That's equal to 6. So the overall order of this reaction is 6. Okay, now I'm going to finish up and put these numbers, the order of the reactants, in the correct order with the correct reactants, and I'm going to write the correct rate law. Okay, and here is the correct rate law right there. Okay, everybody should get that. Hopefully that makes sense. What I've done is replace the X, the Y, and the Z with the appropriate orders of each of the reactants, 1, 2, and 3 respectively. It just happens to be in 1, 2, 3 order. Okay, that doesn't always happen that way. It just happens to be that way. Okay, the next thing that we're trying to do is solve for the rate constant, because we just derived the rate law, so now we need to solve for the rate constant. So what we're going to do is we're going to pick any one of these 7 experiments, and any one of these 7 experiments, and plug in the values for the rate, the concentrations of all 3 reactants, and then derive the rate law mathematically. Okay, and what I have done is I have done this right here, and I have derived the value of the K, and I've used experiment number 7 data. Why experiment number 7 data? It really doesn't matter. You could have used experiments 1, 2, 3, 4, 5, or 6 other than experiment 7, like I have done right here. So I've taken the values for experiment 7 and plugged those in. Again, if you want to, if you're having problems with combining the math and the units together, then separate the math in one column and then do the units in another column and then solve for them by solving for K. So I'm going to rearrange what I need to do right over here and solve for K, bring K to one side and solve for it mathematically with a numeric value and also with the units, and then I'm going to get this value right here. The value for K, that is the rate constant, is 5.25 times 10 to the 5 liters to the 5th power divided by moles to the 5th power times seconds. Okay, and that is the rate constant. Hopefully that worked out well for you. Now, knowing that rate constant and the rate law, I can actually derive the rate for at 26 degrees Celsius, because that rate constant is specific for 26 degrees Celsius. I can derive the rate for any concentrations other than what is given here in experiments 1 through 7. You throw out any other concentration values for all 3 of those reactants, and then we can derive the rate knowing that rate constant and that rate law. Okay, hopefully that problem worked out really well for you. That was a super cool example, and I got a little bit more for you here, so don't cut off quite yet. Okay, I got a little bit of elemental humor here for you, so hang on to this. This should be fun. So what does one do if one can't swim? It's elemental humor. So you got to look at the periodic table for the answer for that, and of course you would sink if you can't swim. Okay, here's some more. What did the cowboy do with his horse? What do you think? Again, of course, it's elemental humor. It's right here on the periodic table, and of course, he rode him. That's what the cowboy would do. And then one more here, I believe. What did the gambler do with his cards? Again, elemental humor. He palladiumed the cards. Awesome. Fantastic. Hopefully you enjoyed those. Hopefully you can share those at your dinner table maybe or something like that. Tell your parents or something. Tell your grandparents. See if they can figure out the answers to those. I am the Crazy Hat Chemist, so I do need a crazy hat. So here's the crazy hat here coming up. Bam! And I love this hat. This is a super cool hat. I should be driving like a Cadillac or something like that with this. So I'm going to see you next time. I hope you enjoyed that video. Give me a thumbs up if you like that video. Subscribe to my YouTube channel, and I will see you next time for more kinetics problems. Bye for now.